In this lab, students use tracker to observe an object falling. They then use Newton's second law to create two computational models of an object falling. One of the models took only gravitational force into consideration, while the other model also considered drag. Finally, students compared each of the models in a graph. First, students recorded and analyzed a video of an object falling. In this case, a plastic bag was used. By observing and plotting the bag falling down the y-axis, students could see how quickly the bag was falling. Next, students create a computational model of the object falling while only considering gravitational force and not drag. Students began by changing the mass of the object to the mass of the plastic bag. They then found the initial position vector from the first data point found in tracker. Next, they set the initial velocity vector equal to 0 since the object fell from S. Finally, students set the delta t value and the g value. In this case, delta t was set as 0.01 and g was set to 9.8. Once the initial conditions were set, students used Newton's second law to model the object falling. Newton's second law states that final velocity is equal to initial velocity plus net force over mass multiplied by delta t. This was used to find the velocity that the object fell at each time increment. Position can also be found using the equation final position is equal to initial position plus velocity multiplied by delta t. This equation was used to find the new position of the object at each time increment. The net force was found first by only taking gravitational force into consideration. This was found by multiplying the object's mass by the g value in the direction the object was falling. Thus, the net force in this model is the weight force. Finally, students added vector arrows to represent the forces. After students had created a model that only took gravitational force into consideration, they had to create a model that also took drag into consideration. When making this model, the initial conditions were almost exactly the same. The only thing that changed was that the proportionality constant, b, had to be found. This was found using a guess and check method, where the last data point of the computational model had to match the last data point of the observed model. Once this constant was found, it was multiplied by the object's velocity to get the drag force on the system. Then, the net force was set equal to the weight force plus the drag force. Since Newton's second law takes net force into consideration, this would change the model, since velocity and position of the object would change. After all three models were created, the data points from each model was collected and put on one graph. As seen, the observed model and the computational model that considered drag had extremely similar data, while the computational model that only considered gravitational force was very different, showing a greater downward slope. This is most likely due to the fact that a plastic bag was used, since a plastic bag is very light and catches a lot of air when dropped. Thus, drag would have a significant impact on the model. Terminal velocity is when the drag force is equal to the weight force, and thus velocity is constant. In other words, acceleration is zero. This can be seen using Newton's second law, which states that final velocity is equal to initial velocity plus net force over mass multiplied by delta t. If drag force is equal to weight force, net force will be equal to zero, and thus final velocity is equal to initial velocity. In other words, velocity is constant. When velocity versus time graphs are created using the data from all three models, it is seen that the models that take drag into consideration show terminal velocity almost immediately. This is most likely due to the fact that a plastic bag is greatly affected by drag and would hit terminal velocity very quickly. Since a computational model that only considers gravitational force does not consider drag, this graph will never show terminal velocity, since net force can never be zero in this model. In this lab, the object was dropped from rest. However, if the object was initially thrown downward, it would not significantly change the terminal velocity data. This is because terminal velocity is reached when the net force is equal to zero. This is achieved at a certain velocity, when acceleration is zero. Thus, the object's ability to reach terminal velocity and the terminal velocity itself would be unaffected. In the computational model without drag, when the initial velocity is non-zero, the model still shows no terminal velocity, since net force still cannot be zero. In the model with drag, when initial velocity is non-zero, the terminal velocity is shown to still be the same. Overall, in this lab, students used Newton's second law to create computational models of a falling object that took gravitational and drag force into consideration. Students compared these models to observed models and saw the effect drag has on a falling object. Finally, students explored the idea of terminal velocity. If I were to improve this lab, I would probably observe a heavier, more condensed object in order to observe an object that does not almost immediately reach terminal velocity when dropped. This way, a more natural curved dataset could be observed.